So let's talk a little bit about our quartic functions. So a quartic function is one of the polynomial. We have an x to the fourth in the mix now. And of course that can't be equal to 0. So here's 3 types of quartic functions, and each one of these kind of show us something different that's going on. This one right here is actually just x to the fourth power. So it almost just looks like a flattened ended parabola a little bit. Or if things are even, they can look like W's. This and all of these I want to point out, or both of these, they have both ends going up. So just like an x squared, they're a happy graph, or A is positive. A is positive. And here, this is not. This is going downward. So A is negative. And again, we can talk about end behavior. Both sides are going up. So in a quartic function, both sides go up or down. So up if A is positive, down if A is negative. So A is positive, we have one x-intercept, and we have one turning point. Here, A is positive, we have 1, 2, 3 x-intercepts, and we have 1, we turn around once, twice, 3 times. 3 turning points. And on this one, A is negative because our end behavior is downward. And we cross the axis twice. So 2 x-intercepts. And we have 1 turning point. That's not another one. So we have 1 turning point. So all of these interesting things that can happen with quartics. And this isn't all either, of course. So, once again, we have a situation where either both ends open up, in which the leading coefficient is positive, or both ends open down, in which the leading coefficient is negative. And then, of course, there's variations in the curvature in the middle of it, but that's all we have. So we solve this, we can do this, we can do this, we can do that, we can do this. I mean, there's so many different things that these things can do that it's just about too many. So once again, the graph of a polynomial function of degree n has at most n minus 1 turning points. So remember that our 4, we have degree 4, we actually have 1 or 3 turning points. Then the graph of the polynomial function of n degree has at most n x-intercepts. So we can have up to 4 x-intercepts. So if I have one that goes like this, and there is where the x-axis is, I have 1, 2, 3, 4. And then the end behavior, if it's an odd degree, 1 comes up and 1 goes down. And if it is an even polynomial, both ends up and both ends down. And we have at least 1 turning point anytime we have an even degree, because it has to turn around and go back up the way that it came. So here is a chart that kind of helps you with that. I love this chart. So linear either has a positive or negative slope. Degree is 1. Turning point 0, it never turns. And the end behavior, if it's positive, leading coefficient, so if the coefficient of x is positive, of course we're increasing all the time. If it's negative, we're decreasing. And it's an odd degree. Quadratic, we either have happy or sad graph. Positive or negative leading coefficient, that the x squared, whatever the coefficient of x squared is. It's a second degree. It has 1 turning point, and its end behavior is either up or down, and it's even. So a cubic of degree 3, it has either 2 or 0 turning points. It can't have 1 because it has to, if it turns at all, it has to turn again. And here's our end behavior, one side up, one side down. The right side's up if it's positive, the right side's down if it's negative. And then the quartic can do all of these weird looking things. 3 or 1, it's either always up, both sides are up, or both sides are down because it's an even degree. So now what we're going to do is just look at this. The complete graph of a polynomial function is shown. How many x-intercepts does this graph have? 2. How many times does it turn around? 1. Is the lead coefficient positive or negative? That's what that says under here that you can't see. Well, it's pointing downward, so the lead coefficient is negative. Is the degree of the polynomial odd or even? Well, the end behavior is going in the same direction, so it is even. What is the minimum possible degree? Well, the minimum possible degree is 2. I think, but a caveat, but it looks more like 4. So, that is the minimum possible degree that you can have. So let's try another one. Let's look at this graph. What is the number of x-intercepts that it has? 1, 2. The number of turning points? 1, 2, 3. Is the lead coefficient positive or negative? Well, right side is up, so we are positive. Is it odd or even? Both sides are going in the same direction, so it's even. Well, due to the 3 turning points, this has to be, the minimum possible degree this can be is 4. So this is 4 or more degrees. Let's look at this one. So here we have a function. What is the number of x-intercepts? Well, looks like 1. Turning points? 0. Is the lead coefficient positive or negative? It's going up, so it is positive. Is this odd or even? So it's going down on one end, up on the other, so it is odd. What is the minimum possible degree? Hope you're saying 3 in your head. Could be 5, 7, I don't know. Okay, let's look at this one. Number of x-intercepts, 1, 2, 3. Number of turning points, 1, 2. Whether the lead coefficient is positive or negative, we're going up on this side, so we're positive. We're going up on one side, down on the other, so this is odd. So what is the minimum possible degree here? Well, 3 intercepts, 2 turning points. The lowest that can be is 3. So it's a cubic or more. Okay, let's do another example. That is the last one. Okay, so the above function can be used to model the number of people covered by Medicaid from 2000 to 2015. Oops. So let's write this in here. Negative 4.457. And there are no shortcuts for this. X to the 4th. And I have to just hit the side key. Plus 130.1 x cubed, I have a shortcut for, math3, minus 1192x squared, plus 5177x, this is a complicated one, 32354. Okay, so let's graph this function for the years 2000 to And it says here also that this is in thousands also. So X is the number of years after 2000. I don't think X is in thousands, but I think the number of people that are covered by the Medicaid is in the thousands. So we're going to graph this for years 2000 to 2015. So I'm only going to need 0 to 15. But what am I going to need for this? Well, let's think about if X is 0. If I put 0 in here, the answer would be 32,354. Oops, that's my scale. I don't want that. Keep that as one. That would have 32,000. So I'm not sure if that is the minimum or the maximum. So I want to be around and close to that number. So let's just do 10,000 to 60,000 and see if that works. And it does. There we go. It does work. 10,000 probably is a little bit high. And we could probably fix our scale on this one to maybe, I don't know, at least 1,000 might look better. We could probably make that 20. Okay. So here's our model, and here's what it looks like. So this is graphing this function. Again, I used 0 to 15 for the x's, and then I used 20,000. I don't have room for that. I did 20,000 to 60,000 for the y's. So what does the model estimate the number of Medicaid recipients to be for the year 2010? Okay, so that is just x equals 10, right? So when x, all we have to do is go to value x equals 10. And then y is 50454. In what year does the model indicate the number of Medicaid recipients to be 40 million? Okay, so we know that this is a little bit harder. 40 million, let's write that out. 40 million is also equal to 40,000, right? Which means what we need to do is we need to figure out when y is 40,000. What is x? So the easiest way to do that is to just do another plot at y equals 40,000. And let's graph it. And let's find its intersection. So now we're going to go calc, intersection, first curve, second curve. And now we move the little cursor until we get really close. We're getting closer. About there somewhere. And we found out that x is just about 2.73. So that was about 2003. It's about as close as we can get. In what year does the model expect the number of Medicaid recipients to be a maximum? So now we need to find what this is up here. So I'm actually going to go back and turn off this plot, or just clear it. We don't really need it. And once this is drawn again, let's go, here's our maximum right here. So let's go second calc, our maximum number 4. We need our left bound. So we're going to go up here. We get close to it. Now we need a right bound, so we have to go make sure we go all the way past where it is flattened out. And that's good. And I know it's hard to see because it's right underneath those numbers at the top. That's a good spot. And it says our maximum is at x equals 13.66, I guess, and y is 57,000. So that's about 57 million people. So x is about 14 years, so about 2014 is when we had the maximum. So does this make sense, or would another, maybe cubic model be more appropriate? So is it likely, as population is increasing, that we're actually going to have fewer number of Medicaid recipients, or should it keep increasing? Well, some of that, of course, depends on politics and what state you live in and a lot of other things. It's hard to predict the future, again, so possibly. I can see Medicaid going down. I can see it coming up. We can see a lot of different things happening. We don't know what's going to happen in the future, but maybe a different model would be more appropriate, one that continued to rise. Simply because of the population increases. Okay. And so that is it.